right, welcome. Today we're going to be talking about section 0.1, real-time computing for a specific mechatronic system. Let's get started. As usual, if you want to take a look at the book website, rtcbook.org, there's a bunch of material on there, a bunch of resources, including the slideshow and information on how to acquire the book on there. All right, so real-time computing for a specific mechatronic system. The T1 target system, that's what we're calling our target system. The T1 target system is a mechatronic system designed for precise control of angular velocity or position, featuring an electromechanical subsystem, a user interface UI subsystem, prototyping hardware, which we can think of as a subsystem, and a real-time target computer. So that's the target system. It's the hardware. It's what we're trying to control when we do our lab exercises at the end of each chapter. And we're using that as a test bed for the ideas that we're learning in this course. At the core of the T1 target system is the MyRio 1900 target computer. This is a target computer that's made by National Instruments. It's a single board computer, which operates using an RTOS, which is a real-time operating system. It's real-time Linux, and we'll talk more about it as we proceed. The electromechanical subsystem includes a DC motor connected to a flywheel, which is an inertia load, and driven by a current amplifier, which the target computer controls. So over here in the diagram, we can see that we have a motor, we have a flywheel connected to the motor that's rotating. We have an encoder on the motor, a current amplifier that supplies power to the motor, a power supply that supplies power to the current amplifier. All of this collectively we call the electromechanical subsystem. The real-time target computer, the MyRio 1900, is what controls the amplifier and gets feedback from the encoder about the angular position of the DC motor and the flywheel, which is attached to the shaft of the motor through a coupler. We also have the user interface subsystem, which we're going to spend a good deal of time learning to program as well. The keypad and a display. We have the prototyping hardware, which include an interrupt switch, and testing hardware, which we will occasionally be using in some of the lab exercises. More on that later. And then all of this together we call the T1 target system. Interacting with that is the D1 development system. The numbers correspond, D1 and T1. D for development, T for target, which consists of a development computer, a virtual machine, and an IDE. We're going to get more into that in just a moment. We're focusing right now on the T1 target system. The D1 development system is how we program this target computer. Okay, good. The UI subsystem, which I mentioned right here, includes a keypad and display, and is the focus of lab exercises 1 to 3. So while we're getting to understand the development environment and the C programming language, we'll be working on the user interface subsystem in the first few labs, and then later on we're going to move on to controlling the motor position and velocity. So we start off with the keypad and display and move on to the amplifier and the motor. The development system, comprised of a PC, a virtual machine, and an integrated development environment, are used to program the target computer, which can then function independently. So once you've finished your programming tasks of this target computer, you can disconnect this and the target computer will run the program independently. So that's the idea. Okay, we're going to go into each of these subsystems a little bit more in the rest of this lecture. So the real-time target computer subsystem Real-time target computer controls the electromechanical subsystem, determining actions like the current to apply to the motor based on real-time input and system safety. So this is a picture of the MyRio with its enclosure taken apart. So we've opened it up and we can see the board. We can see this is a system on a chip. We'll talk a little bit more about what that entails a little later on. But that is the sort of heart of this board and this computer. We have some connectors, so connectors A, B, and C, and these will allow us to connect to the peripheral components, so including connections to the amplifier, connections to the user interface devices, etc. Power comes in here. There's a USB connection here, and that's how we're going to program the board, is through a USB interface. Real-time computing controls latency, which is the delay between input changes, for example, sensor readings, and output responses, which must be minimal for systems with fast-changing dynamics. That's the real-time aspect of this, right? We have a computer that's interacting with a real physical system, in this case a motor with a flywheel on it, and that's not waiting around for anyone. So once we have an update on our measurement, say the angular position of that flywheel, we're going to want to immediately take action. So the time that elapses from when we take that measurement to when that action is taken is latency. And so we want to control it. We usually want to minimize it. Yeah, that's the essence of real-time computing, is controlling that latency, usually making it as short as possible, but also interacting in a predictable frame of time, in a predictable duration of time from when the measurement is taken. Key elements of control include user commands, for example, setting the target RPM, angular velocity, programming, defining control algorithms, and feedback, using sensor data to adjust outputs dynamically. So we're going to do all of those as we proceed. The target computer is the MyRio 1900, which features an ARM Cortex-A9 processor, which is included in the system on a chip, the SoC, for general programming, and an FPGA for fast input-output tasks like encoder rotation counting. FPGAs are actually, they're called fully programmable gate arrays. They're pretty general devices that can be used to emulate a lot of different digital hardware. However, what we're using it for mostly is for really fast input and output. So we're not going to be programming the FPGA in this course. The FPGA is going to be operating in the background and doing tasks like counting the encoder pulses for us. So it's a really nice aspect of the MyRio board. It's one of the reasons why we use it. The MyRio runs real-time Linux, real-time operating system, and supports programming in C, which will be our primary programming language in this course. The board actually also allows you to program in a really high-level language called LabVIEW. It's a graphical programming language, but we're going to be programming it in C, which is the lingua franca, as we'll talk about it, of the real-time computing and the embedded computing, closely related field, world. So C is the language that most people use, and that's what we'll use as well. And we'll talk about why. The user interface subsystem, UI. So in general, these are types of input devices. So here are some examples. You're familiar with these and others. Here's an array of buttons. Here's a keypad. Here's a keyboard. So these are some common types of input devices. Here's what we're going to be using for our target system, the T1 target input device is going to be a keypad with this arrangement of numbers and some different tasks or functions that these other ones will have, corresponding to characters or other actions. So 16 buttons, each labeled with a number or symbol. We're going to program these buttons to correspond to the labels shown. Actually, this keypad, when you get it on the website, there's information about how to get a keypad. It doesn't have pre-specified characters for these. You actually put the labels on the keypad yourself. We're going to use this layout, but we're going to be programming this button to mean 1, this button to mean 2, etc. So that's the layout we'll use, and we'll get into the low-level driver writing for this input device. Okay, in general, types of displays. So user interface involves not just a user input, but also output to the user. So here's how we get information to the user. We get information in these types of displays. This is one of the ways. We could also use an LED light blinking, for instance, but these are a little bit more advanced user displays. And so 14 segment display is one that you will see occasionally on like, for instance, if you've ever gone to a sporting event that has a reader board, you'll see these sort of segment displays. So there are 7 segment displays. There are even higher number of segment displays as well. You'll see occasionally. There are dot matrix displays, so you can interact with the computer through a display that has a bunch of dots, so dot matrix display, and then screen displays which have pixels. So dot matrix display can only present one color at each location, whereas a screen can typically present more colors at each location. Yeah, and also typically has a much higher resolution than a dot matrix display. Okay, we're going to use this sort of dot matrix display. It's a type of dot matrix display that you'll see in a lot of industrial hardware. A little screen that can say, "Welcome to real-time computing for mechanical engineers," for instance, but it can write text, it can write numbers, etc. So the display has 4 rows with 20 characters each. We will program the display to show the current motor velocity and other system information as we proceed through the labs, through the chapters in the book. Okay, did the UI subsystem. Here's the electromechanical subsystem. The T1 target system uses a DC power supply to provide electrical power to the motor. So it's a DC motor. The power supply delivers a fixed current, but the T1 target amplifier regulates this based on control commands. So power supplies are dumb. They can't supply variable amounts of current or voltage. That's what an amplifier does. So an amplifier can be programmed through interaction with a computer, like the MyRio board we'll use. A current amplifier is used in the system, which applies current proportional to the command signal for precise motor control. So we're using this current amplifier. However, throughout the text, we will develop models for both voltage and current control of the motor, because voltage-controlled amplifiers are common, and there are some differences. So instead of just developing the current-controlled aspects for motors, we're going to develop voltage control and current control in parallel, just so that we have an opportunity to learn both as we go through, even though our device uses a current amplifier, which is a little nicer in some ways, as we'll see. Okay, the motor. The T1 target system features a permanent magnet brush DC or PMDC motor, chosen for its simplicity and cost effectiveness. PMDC motors are more straightforward to use compared to brushless DC motors or stepper motors. Those are 2 other options. Stepper motors, while simple and inexpensive, are unsuitable for precise or continuous motion control. For instance, if you're controlling for a velocity, it's really a poor choice. For precise motion control, it depends on what you mean by precise, but they have a fixed number of angular positions, stepper motors do, that they can be in. So sometimes that's sufficient. In some applications, that'll be sufficient, and others it won't be. So it just depends. The motor, coupled with the amplifier, drives a flywheel that serves as the system's inertial load. So the motor, amplifier, drives a flywheel that serves as the system's inertial load. So we've got the motor that's being driven by an amplifier. The motor has connected to its shaft a flywheel, and that's what we're going to be moving around. It's easy to control a motor that doesn't have a load on it. So putting a load on it makes it more realistic. So we'll just put a flywheel on it. Okay. All right, closed loop control and lab exercises. The closed loop system adjusts motor current based on encoder feedback. Remember, we saw we had an encoder on the back of the motor, and that encoder is going to provide us feedback about the angular position that the motor is currently at. So with this feedback, comparing user commands, what's the commanded angular position, with actual measurements of that angular position. So this is the way that we like to draw this, and we'll talk about what this is. This is a block diagram for a feedback control loop. I'm not assuming that you've seen this type of thing before. We're going to go into some control theory in some of the later chapters to introduce these. The main idea, though, is that we have a motor and a flywheel here, which we often call the plant we want to control the output of. The output here is the angular position. We take a feedback measurement with an encoder of that angular position, feed it back to the target computer. The target computer takes a user's command for what that angular position should be, subtracts out what the actual measurement is from the commanded value, and the difference is the error, right? We would like that difference to be 0. In any case, though, we're going to feed it into the controller, which is going to decide what the control effort should be into the motor and flywheel, given that we have a certain error. That controller actually implements that control effort by signaling the current amplifier, which supplies current to the motor in accordance with what the controller wants to do at that point. So we'll learn how to design the controller and implement it in programming throughout this course. Angular velocity control begins with open loop control in lab exercise 4, which means we're not going to get the feedback, and evolves to closed loop control in lab exercise 7. So we'll do angular velocity control in lab 7. We have to build up some blocks to get there. Position control of the flywheel is explored in lab exercise 8, utilizing encoder feedback for precise adjustments. Appendix A in the book provides a detailed description of the target electromechanical subsystem and its components. There's also some information on the website about that and the setup of that. Okay, finally, the prototyping and testing hardware. Prototyping and testing hardware is essential for system development, debugging, and testing. Common laboratory tools, such as an oscilloscope, are used alongside specialized components like NAND gate integrated circuits for tasks like switch debouncing. We'll talk about that in a later chapter. Mechanical switches are employed for prototyping tasks, including triggering finite state machine transitions and interrupts. Again, we'll talk more about it, but this is some of this extra hardware that we'll use, also described in Appendix A and on the website. So you're going to need those things if you're at a university. Hopefully and most laboratories will have these things. These specific gates you might need to order, but they're inexpensive parts. The more expensive things will be like the oscilloscope that we need. So, all right. Well, that is it for this section. I'll see you next time.